Hello everyone, I'm Rundong Li, a second-year PhD student from Xi'an Jiaotong University. It's my pleasure to talk about our work, building fast and compact sketches for approximately multi-site multi-membership query. This is a joint work with Pinghui Wang, Jiongli Zhu, Junzhou Zhao, Jia Di, Xiaofei Yang, and Kai Ye. Here is the outline of my presentation. Let me start from the introduction. Membership query is a popular research topic in data science. Given a set S and a query element E, the goal is to answer whether E belongs to S. Membership query widely appears in many applications from different areas. For example, in networking, membership query can be used for web caching and network monitoring. In database, membership query can be used in key value storage. Besides, membership query can be used in other areas such as mobile computing. There are sketch methods for effective and efficient membership querying. For example, the Bloom filter uses a bit array with a set of independent hash functions. Elements in the set are mapped into different bits. A query element is claimed to be in the set if its corresponding bits are 1. Other example includes the cuckoo filter, which uses partial key cuckoo hashing. The cuckoo filter maps elements to fixed length fingerprints and stores them in a hash table. In the query phase, if the fingerprint of a query element is matched, then the element is claimed to be in the set. In this paper, we study a more complex problem named multi-set multi-membership query. Given n sets from S1 to Sn and a query element E, the goal is to answer in which sets E exists. Note that E can exist in multiple sets. Multi-set multi-membership query also has wide applications. For example, in multi-level storage systems, such as the log structured merge tree, multi-set multi-membership query helps reduce the number of accesses to find data item of interest. Another example is DNA sequence search. Genomic sequence data are stored in public archives with huge volume. Given a DNA sequence of interest, multi-site multi-membership query helps fast locate possible archives that contains the DNA sequence, and thus saves a lot of time for the follow-up research. Current method to address multi-site multi-membership query is to allocate a sketch of membership query for each set. For example, BigSci allocates an identical Bloom filter for each set. During query phase, BigSci checks n filters to determine the membership set. The query speed is linear with the number of sets, which is unacceptable for a large n. To reduce the number of filters to be checked during query phase, a recent work Rainbow proposes to map n sets into B partitions and allocate each partition an identical Bloom filter. To reduce false positives, Rainbow repeats the random partitions independently for R times. Totally, there are RB filters to check in the query phase. As the brief example shows, a Rainbow maps 3 sets into 2 partitions. Set 0 and set 2 are in partition 1, and set 1 is in partition 2. Each partition corresponds a Bloom filter. To insert element X from set 0, Rainbow inserts it into the Bloom filter of partition 1. To query an element Q, Rainbow queries Q in 2 Bloom filters and returns partition 2 since it reports the existence of Q. Then sets mapped into partition 2 are reported as the membership set of Q. To further reduce false positive, another repetition is used, and we take the intersection of results reported by each repetition to get the final membership set. However, we observe that most real-world data sets are heavily screwed. That is, a few sets contain many elements, and most sets contain relatively a few elements. In this situation, the load factors of Bloom filters in Big Sign and Rainbow are also heavily screwed. Bloom filters for large cardinality sets are congested, which leads to a large false positive rate. Meanwhile, Bloom filters for small cardinality sets are sparse, which leads to a serious waste of space. So how to achieve higher space efficiency as well as keeping high accuracy and fast query speed? In this paper, we designed a CFC framework for multi-site multi-membership querying. The CFC framework achieves higher memory efficiency as well as faster query speed and higher accuracy. Besides, the CFC framework can integrate with mainstream membership querying sketches. In this paper, we use the Bloom filter and the Cuckoo filter as 2 instances. Moreover, the CFC framework achieves cheap updates for streaming inputs and emerging sets. Specifically, like Rainbow, CFC also maps N sets into B partitions in advance. To insert an element X from set Si, CFC encodes HX as an anchor and GI as an offset. To reduce false positives, we further use R-independent repetitions. For an emerging set as n+1, we first map set n at +1 to partition G n+1 and insert elements from set Sn+1 correspondingly. To obtain the membership set for a query element Q, we query Q in R repetitions. Specifically, in each repetition, we first map Q to its anchor location HQ, and then check the next B consecutive locations, which represents that B partitions probably containing Q. For partitions reporting positive results, we take the unit of them as the results of the repetition. We then take the intersection of R repetitions as the final membership set. And in this paper, we use the Bloom filter and the Cuckoo filter as 2 instances of our CFC framework. There are several good properties for the CFC framework. At first, CFC achieves high memory efficiency through shared space. All sets are compressed into a shared sketch, and elements are distributed evenly. Therefore, space congestion in large cardinality sets are alleviated, and wasted space in small cardinality sets are effectively used. Second, CFC achieves higher query speed by good locality in storage. In the query phase of element Q, we first map Q to its anchor location HQ. Starting from HQ, we check the next B locations to determine the existence of Q. During this process, since the B locations are consecutive, we need fewer memory accesses and thus faster query speed. Moreover, CFC achieves higher accuracy by higher memory efficiency and the repeating and merging technique. Due to the higher memory efficiency, there are fewer false positives on large cardinality sets, and the expected false positives on small cardinality sets still meet the demand. As for the repeating and merging technique, we define delta as the ratio of error without the technique to the error with the technique. Here, B is the number of partitions, R is the number of repetitions, and V is the multiplicity, representing that an element exists in V sets. Delta values greater than 1 means the superiority of the repeating and merging technique. We fix other parameters and analyze it theoretically. And we can observe from the result that repeating and merging technique greatly improve the accuracy for smaller multiplicities V. In the evaluation stage, we use 4 datasets. 2 of them are real-world datasets for multilabel classification, and 2 of them are extracted from real-world DNA archives. We list the competing methods in our experiments. In Bloom filter-based method, CSC Big Sign is CSC Bloom filter without the repeating and merging technique. CSC Rainbow is CSC Bloom filter with repeating and merging technique. Besides, we noticed that a recent method, shifting Bloom filter in VLDB16, is actually the same method as CSC Big Sign. In Cuckoo filter-based methods, NCF allocates each set an identical Cuckoo filter, and CSC NCF is CSC Cuckoo filter without repeating and merging technique. As for metrics, we use the number of false positive sets and query speed as the metrics to evaluate the accuracy and efficiency respectively. All methods are compared under the same amount of space for sketches. At first, we conduct experiments on dataset RCV1 to determine the parameter B and R. We observe that smaller B leads to large false positive sets, and large R leads to small false positive sets and high query time. In summary, we set B equals to n divided by 10 and R equals to 3. For Bloom filter-based method, we first evaluate the influence of memory budget. We generate 1,000 non-existing elements as queries and observe that the CSC Rainbow and CSC Big Sign are more accurate than Rainbow and Big Sign respectively. And CSC Rainbow is more accurate than CSC Big Sign due to the repeating and merging technique. As for efficiency, CSC Big Sign and CSC Rainbow are slightly faster with the increase of memory budget. And CSC Big Sign and CSC Rainbow are faster than their counterparts respectively. This shows that CSC framework effectively improves the query efficiency. Moreover, CSC Big Sign is faster than CSC Rainbow, since the set union and set intersection operations in CSC Rainbow are computational bottleneck. We further analyze the influence of element multiplicity. Specifically, we randomly insert 1,000 unseen elements into V sets and use them for query. We observe that the CSC Big Sign reports fewer false positives than Big Sign, and both of them are not sensitive to element multiplicity. However, the false positive sets of Rainbow and CSC Rainbow increase with V, and this is caused by the random partition. But the performance is still excellent for small V. As for efficiency, CSC Big Sign and CSC Rainbow are faster than their counterparts. CSC Big Sign is slower with the increase of V. This is because there are more membership sets to detect. CSC Rainbow and Rainbow are slower with the increase of V. This is because it needs more time for set union and set intersection operations. For Cuckoo filter-based method, we conduct experiments on dataset DA500, and the results are similar to CSC balloon filter. Finally, we compare CSC balloon filter with CSC Cuckoo filter on dataset RCV1 and observe that CSC balloon filter has faster query speed, while CSC Cuckoo filter is more accurate. As a summary, in this paper, we propose a CSC framework for multi-site multi-membership query. The proposed framework has higher memory efficiency, faster query speed, and fewer false positives. The CSC framework can be integrated with most mainstream sketches, membership querying sketches, such as the balloon filter and the Cuckoo filter. We conduct theoretical analysis as well as extensive experiments, and experiment results shows the superiority of our CSC framework. And that's all. Thank you.